Good morning, everyone. Thank you for being here today. We're excited to share our presentation with you. I am Mario, and I'm joined by Nicky, Xiaoling, and Yoselin. Our topic focuses on one of the most fascinating figures in science, Erwin Schrodinger, and his famous experiment, the Schrodinger's cat. Throughout this presentation, we'll explore who Schrodinger was, what his contributions to quantum mechanics mean, and how reliable the Schrodinger's cat model really is. So sit back and join us as we dive into a strange and intriguing world of quantum theory. Let's get started. Erwin Schrödinger was an Austrian physicist born in 1887 who became one of the most influential figures in quantum mechanics. He is best known for developing the Schrödinger equation, a fundamental equation that describes how quantum systems evolve over time. This work earned him the Nobel Prize in Physics in 1933. Schrödinger also introduced one of his most famous experiments in science, the Schrodinger's cat. It was designed to show the strange nature of quantum superposition, where a system can exist in multiple states at once until observed. Beyond physics, Schrödinger explored philosophy and biology, even writing a book called What is Life? His ideas continue to shape science and inspire curiosity today. Erwin Schrödinger wasn't just a physicist. He was a thinker who challenged how we understand reality.
Okay, let's go on the Schrodinger proposals. The Schrodinger's cat's thought experiment illustrates the paradox that arise when applying quantum mechanics to everyday object. In the setup, a cat is placed in a sealed box with a radioactive atoms with a Geiger counter, a vial of a poison, and a hammer mechanism. If the atom decays, the detector triggers and releases poison. The cat dies. If there's no decay occurs, the cat survives. According to quantum the quantum theory, before observation, the atom exists in a superposition of both decay and non-decay status. As a result, the cat is also in a superposition of being both alive and dead until the box is opened and a measurement is made, which causes a wave function to collapse into a defined state. Through this experiment, it challenges the classical institutions and arises the question about the role of observations, the nature of measurement, and whether the quantum rules apply at the microscopic scale.
Okay, now for the expansion of the thought experiment. In 1927, Bohr introduces complementarity. Certain quantum properties, like wavelength or particle-like, cannot be measured simultaneously, which is what Bohr proposed. Einstein's objection proposed a thought experiment to expose contradictions in complementarity. Einstein's thought experiment involves the particles passing through a double slit, which interferes wavelength behavior. Before reaching the double slit, particles pass through a single slit on springs. The momentum then transfers to the slit, revealing particle-like information.
So, what's the relation to quantum mechanics? How does this little critter relate to what we've learned in class? So, Schrodinger's cat illustrates the concept of quantum superposition. So, like electrons and orbitals, the cat exists in overlapping states until measured. We don't truly know how something behaves even when making an observation. So basically, we're just seeing one of the many probabilities. It's also important to note that Schrodinger's cat experiment also highlights quantum versus classical mechanics. So classical systems are deterministic and predictable. So as we can see in our little image right there, we can come up with a formula and we'll be able to predict the results. However, when it comes to quantum mechanics, these systems are more so probabilistic. Observables exist as probabilities until observation. Essentially, when connecting this to Schrodinger's cat experiment, we don't know whether the cat is dead or alive until we open the box. So now of this cat experiment. So the thought experiment was interpreted and discussed in many ways. Scientists simply just couldn't agree to one application. Essentially, Schrodinger's cat is the divorced child to the child of divorced parents for many scientists. So anyways, here are just a few interpretations. In the Copenhagen interpretation, wave function represents all possible states. When we take a measurement, we witness the collapse of the wave function. In the many-world interpretation, it suggests that all outcomes occur simultaneously in parallel universes. Essentially, in one universe, there is a living cat, while in the other, we have a dead cat. Thirdly, we have the objective collapse interpretation. This interpretation suggests that quantum systems naturally collapse due to the intrinsic physical mechanisms rather than observation. In other more simpler terms, superpositions collapse naturally without observation. Although each interpretation offers a different viewpoint to this feline madness, they all point back to the same core principle. This core idea is that quantum systems remain undefined until measured, raising fundamental questions about how quantum behavior becomes classical reality.
Schrodinger's cat isn't a real experiment. It's a thought-out experiment. Schrodinger created it in 1935 to highlight the strange implications of quantum mechanics, especially the concept of superposition. In this scenario, a cat is placed in a sealed box with a mechanism that depends on a quantum event. Until the box is opened, the cat is considered both alive and dead at the same time. But here's the thing. Schrodinger never meant for this to be taken literally. It was designed to criticize the Copenhagen interpretation, which suggested that particles exist in multiple states until observed. So, is Schrodinger's cat reliable as a scientific model? Not really. It's not a practical experiment. It's a metaphor. Its purpose is to make us think about the limits of quantum theory and observation, not to describe reality for large objects, like cats. Today, physicists use it as a teaching tool, not as evidence. It's reliable for illustrating quantum weirdness, but not for predicting real-world outcomes. Schrodinger's cat is a paradox, not a proof. It reminds us that quantum mechanics challenges our intuition, and that's what makes it fascinating.
Okay, now for the modern-day experimental applications of Schrodinger equation. So machine learning, aka AI, combines the speed of classical potentials with the accuracy of quantum mechanics, transforming in silico experiments into data-driven problems. Today, there are many different types of applications, but we're going to talk about the Hetrick Fock and post-Hetrick Fock methods. They use a single Slater determinant, but this error is chemically significant, limiting the HF's accuracy for real applications. While post-Hetrick Fock method includes electron correlation by the energy, lowering beyond HF due to electron-electron interactions. Density functional theory is used for molecular structure, bonding, reaction energies, kinetics, and also spectroscopy. The pros is that it reduces a three-dimensional wave function problem to a 3D density problem. But the con is that it's strongly correlated with systems. It has dispersion with van der Waals interactions as well as excited states. Semi-empirical methods are methods that simplify quantum mechanic calculations by introducing empirical parameters into the equation, while classical potentials describes molecular systems using parameterized classical potentials, enabling large-scale simultaneously. Although it cannot describe bonds breaking or forming or any electronic effects. Data-driven machine learning is purely numerical models without embedding any physical laws, while physics-inspired machine learning is more into the implementation of speed and accuracy. With neural networks designed with symmetry constraints, machine learning models that correct approximate quantum results. as well as how it predicts chemical properties across diverse systems. The image shows a schematic overview of the hierarchy of physical information in quantum mechanical related machine learning models in silico experiments within the chemistry and material sciences.
So overall, in the Schrodinger cat, it shows how weird the quantum mechanic it is. It demonstrates a superposition being in a multiple state at once and highlights the conflict between the classical and quantum thinking. People still debate how measurement works, and that's why there are multiple interpretations. Today, it is mainly used as like teaching tools rather than actual scientific model. Hope you like the video. Thank you for watching.